Long before rockets reached the sky, people imagined leaving Earth. Visionaries like Tsiolkovsky, Goddard, and Oberth and worked on the math and ideas that made practical spaceflight thinkable. The modern story begins during and after the Second World War. Rockets developed in Germany were the first to reach high altitudes. After the war, many engineers and technologies moved to the United States and to the Soviet Union. Those wartime advances, engines, guidance systems, and high-speed aerodynamics became the building blocks of early space launchers. What had been weapons were gradually reshaped into carriers for science, satellites, and, eventually, people. In the 1950s and 1960s, the United States organized its first human spaceflight programs: Mercury, Gemini, and Apollo. Each program taught engineers and astronauts essential skills: how to reach orbit, how to rendezvous and dock in space, how to live and work in microgravity, and how to plan safe re-entry and landings. Those lessons were not just technical. They created a generation of engineers who knew how to design complex spacecraft, to test them carefully, and to learn from failure and success. Not everyone wanted capsules that landed by parachute. Some engineers imagined piloted vehicles that would fly back through the air and land on a runway, like an airplane returning from space. These were called spaceplanes. In the 1960s, researchers also explored a close cousin of the spaceplane: the lifting body. A lifting body is a shape that produces aerodynamic lift without full wings, a rounded or stubby body designed for controlled re-entry and gliding landings. Small, unpowered prototypes, the famous M2, F1, and later M2, F2, and HL-10, were built and flown to test how such shapes handled at high speed and during descent. These experiments helped engineers understand how a future winged orbiter might behave in the atmosphere. During the 1960s, the United States military was very interested in space. They imagined small, fast, winged spacecraft that could carry out missions in orbit. Some would take pictures of Earth, others could even intercept satellites. One of the most famous projects was the Boeing X-20 Dinosaur. Dinosaur was designed to be a piloted spaceplane. It would go into orbit and then return to Earth, landing like an airplane on a runway. Engineers worked on it for years. They built engines, guidance systems, and tested materials for re-entry. But the program never flew. In 1963, it was canceled. The government decided that the cost and technical risks were too high. Even though Dinosaur was canceled, it was not a waste. The lessons learned about heat protection, winged re-entry, and piloted spaceplanes stayed in the minds of engineers. These ideas later helped shape the design of the Space Shuttle. Other smaller military projects also explored reusable space vehicles. Some tested lifting bodies, aircraft-shaped prototypes that could glide safely back to Earth. All these experiments added pieces to a puzzle: how to make a spacecraft that could fly to space and return safely, again and again. By the end of the 1960s, the United States had walked on the moon. The Apollo program, from Apollo 1 through Apollo 17, was a vast effort, uniting more than 400,000 people across NASA, industry, and universities. Apollo showed humanity that deep space travel was possible, but more importantly, it created knowledge that future programs would need. From Apollo, engineers learned how to build and test powerful launch vehicles, like the Saturn V, still one of the most capable rockets ever built. They learned how to design spacecraft that could survive the harshness of space, with reliable life support, guidance, and communication systems. They also learned hard lessons about safety. The tragic Apollo 1 fire in 1967 forced NASA to rethink materials, cabin atmosphere, and emergency procedures. Those changes made the later Apollo flights far safer. Apollo proved rendezvous and docking on a large scale, the command and lunar modules meeting in orbit, separating, then joining again. These maneuvers became the basis for the shuttle's role in building and servicing space stations, and Apollo gave experience with re-entry from very high speeds. The capsules survived the searing heat of returning from the moon. That experience informed the shuttle's need for a reusable thermal protection system, the thousands of ceramic tiles that would later cover its wings and fuselage. But Apollo also revealed limits. Each mission was extremely expensive, and the Saturn rockets were single-use. Once a rocket flew, it was gone forever. Policymakers knew this approach could not be the future of routine spaceflight. So, as Apollo drew to a close, the question shifted. How could the United States maintain a strong presence in space, more often and at lower cost? The answer proposed was reusability, a spacecraft that could launch, work in orbit, return to Earth, and fly again. Apollo's triumphs and its lessons formed the foundation. Without the mastery of large-scale rocketry, crew operations, docking, re-entry, and safety gained in the 60s, the dream of a space shuttle could never have moved forward. In early 1972, the United States government gave a clear direction. NASA should develop a reusable space transportation system, a shuttle that could fly multiple times and make access to space routine. The new program promised regular flights and lower long-term costs, though those promises carried large technical and management challenges. Designing such a shuttle required choices and compromises. Engineers debated fully reusable two-stage systems versus a partly reusable stack in which an orbiter would return to land and an external tank would be expendable. Military and civilian needs shaped the program. The new vehicle had to carry long satellites, deploy large payloads, and sometimes meet Air Force cross-range requirements, the ability to return to a runway far from the launch site. These constraints led to the distinctive shuttle design, a winged orbiter, reusable solid rocket boosters, and an expendable external tank. Throughout the 1970s, engineers built prototypes and test vehicles. One visible milestone was the aerodynamic test orbiter, named Enterprise, which never flew to orbit but was used for atmospheric approach and landing tests. In 1977, Enterprise rode piggyback on a carrier aircraft and performed glides and landings to prove that a winged orbiter could be handled safely during atmospheric flight. These tests were quiet, methodical steps toward a much larger and riskier program. The path to the shuttle was not a single straight line. It was a patchwork of wartime rocketry, careful lifting body flight research, canceled military programs, and the hard lessons of Mercury, Gemini, and Apollo. Each piece added knowledge about heat shields, attitude control, guidance, runway landings, and the logistics of maintaining complex vehicles. Those lessons made the Space Shuttle possible, even if the final vehicle embodied compromises that reflected both engineering realities and political needs. After years of development, testing, and careful learning, the Space Shuttle finally became reality. The first flight, STS-1, took place on April 12, 1981. For the first time, a fully reusable spacecraft carried astronauts into orbit and returned safely to Earth. The shuttle program achieved incredible milestones over its 30-year history. It deployed hundreds of satellites, including communications satellites, weather satellites, and scientific observatories. One of the most famous payloads was the Hubble Space Telescope, which transformed our understanding of the universe. Shuttle missions also helped build and service the International Space Station. Astronauts carried modules into orbit, connected them, and performed countless spacewalks to maintain and upgrade the station. The shuttle became a unique platform for science experiments in microgravity, allowing researchers to study materials, biology, and physics in ways never before possible. However, the program faced tragedy. On January 28, 1986, the Challenger broke apart 73 seconds after launch. All 7 crew members were lost. The accident led to a complete investigation and major redesigns to improve safety, especially in the solid rocket boosters. 17 years later, on February 1st, 2003, the Columbia disintegrated during re-entry, again killing all 7 astronauts on board. This disaster reminded the world of the immense risks of spaceflight and led to further safety improvements and procedural changes. Despite these tragedies, the shuttle program was remarkable for its achievements. It proved that humans could repeatedly reach orbit, carry large payloads, repair satellites in space, and construct orbital infrastructure. It demonstrated that reusable spacecraft were possible, a lesson shaping today's private space companies and new generation vehicles. The last space shuttle flight was STS-135, carried out by Atlantis in July 2011. After 30 years, NASA retired the shuttle because the program had become very expensive to maintain, safety risks remained, and newer rocket designs promised lower-cost access to space. Today, the space shuttles are preserved in museums, so their legacy can be seen and remembered. Discovery is at the Smithsonian National Air and Space Museum in Washington, D.C. Atlantis is at the Kennedy Space Center Visitor Complex in Florida. Endeavour is displayed at the California Science Center in Los Angeles. Enterprise, the atmospheric test shuttle, is at the Intrepid Sea, Air and Space Museum in New York City. The Space Shuttle program may have ended, but its lessons, triumphs, and even its tragedies continue to shape the future of spaceflight. It reminds us that reaching for the stars is never easy, but with vision, careful planning, and courage, humanity can accomplish extraordinary things. As you relax and listen to these words, imagine the shuttle gliding silently through the sky, returning home after a mission in the quiet of space. Let your breathing slow, let your mind float among the stars, and know that the story of the Space Shuttle is not just about machines, but about people daring to dream, learn, and explore.